Hello, welcome back. We are going through the Rust programming language book. And here we're going to continue into the section on references and borrowing. So let's jump in. The issue with the multiple tuple code in listing 4-5, which you can look at from the previous section or watch the previous video that we did to cover that section, is that we have to return the string to the calling function so that we can still use the string after the call to calculate length, because the string was moved into calculate length. Instead, we can provide a reference to the string value. A reference is like a pointer in that it's an address that we can follow to access the data stored at that address. So as a first little basic point, technically, a reference is not identical to a pointer, but they are actually very closely related subjects. That data is owned by some other variable. Unlike a pointer, so to really lay out the difference between a reference and a pointer, a reference is guaranteed to point to a valid value of our particular type for the life of that reference. We've already mentioned this little word life right there. We haven't explicitly talked about lifetimes as far as I recall going through this book, but that will be one of the really key concepts to understanding the Rust programming language. Okay, here is how you would define and use a calculate length function that has a reference to an object as a parameter instead of taking ownership of the value. All right, so let's do it. We'll do a little bit of coding here. We'll go S1 is going to be bound to the value of string from hello. All right, and then we're going to say let len be bound to the value of calculate length, where we're going to pass in not S1, but a reference to S1. Now, we haven't defined what that function is, so of course we're getting a little bit of an error from the Rust analyzer. That's all right. We will fix that later. So let's grab ourselves a little print line macro, and with that, we're going to say the length of, in single quotes, just for stylistic whatever, S1 is length. Also in formatted print. There we are. Now we just need to define what this function actually does. Let's go have some fun, and with that fun, we will calculate length, because that's the function we decided to define. Okay, so we've got a reference to string, not a string itself, but a reference to something that has a string type, and we're going to return a usize, which is like an integer, but specialized to the topic of how big is something. And we're going to return s.length. So it's like having a string. If you look at this and it says alloc string pub constant fun length, return the length of this string in bytes. But of course, when we're talking about this ampersand here, this and symbol, we are actually only going to borrow it. We're not going to keep it. We're not going to take permanent kind of ownership of it. Okay, so let's run this little example here. We'll go cargo run, and we should see that length of blah, blah, blah is blibbity blabbity. So the length of hello is 5. Great. Absolutely wonderful. But we're going to take a look at things from a memory kind of, not a detailed layout, but a simplified layout, and see what kind of structure this is compared to the variable names and pointers we've seen so far. So first, notice that all the tuple code in the variable declaration and the function return value is gone. Second, note that we pass ampersand S1 into calculate underscore length, and in its definition, we take ampersand string or reference to string rather than string itself. These ampersands represent references, and they allow you to refer to some value without taking ownership of it. look at figure 4-6 that depicts this concept. So we got 4-6, a diagram of reference to string S pointing at string S1. So you got this S variable that has really just a pointer to S1, which S1 is going to be connected to, or is, a pointer and length and capacity, where the pointer points to the heap allocated memory. So let's take a little note here. The opposite of referencing by ampersand is dereferencing, which is accomplished with the dereference operator asterisk or star. We will see some uses of the dereference operator in Chapter 8. That's not for a little while. We're only on Chapter 4, and discuss details of dereferencing in Chapter 15, which is quite a while from now. Let's keep going, though. Let's be brave. Let's chance it. So let's take a closer look at the function call here. Let's do it. So we've got this let string from hello, and they've got the same there, and we've got the length, calculate length with reference to S1. So let's talk about the thing that's really different from the previous code we've seen in previous videos. The ampersand S1 syntax lets us create a reference that refers to the value S1 but does not own it. Because the reference does not own it, the value it points to will not be dropped when the reference stops being used. This is important. This actually helps us avoid having to write functions that pass through all the data, just so that we can reuse it later. So likewise, the signature of the function uses ampersand to indicate that the type of the parameter S is a reference. Now, let's add some explanatory annotations. I don't know, maybe we'll just read them. So we've put some comments here that S is a reference to a string. Okay, that's true. That we can tell because there's ampersand string rather than string itself. If we do that, you can see we get an error for mismatched type. So whether something is a reference to a certain type versus a type of itself, like string versus reference to string, those are distinct types in the Rust programming language. You must respect that distinction in order for the compiler to accept what you're doing and to be able to have the compiler actually properly validate whether what you're doing is correct. Insofar as this form of type correctness to check whether you're having memory safe access and usage and perhaps changing or borrowing in this case the variable. All right, so let's see what the next thing is that they say here. They say here, S goes out of scope. That's true. When you get to that end curly bracket, you go out of scope. And for heap allocated things, you got the drop method that will run, or for the stack, that it gets popped off of the stack. But because S does not have ownership of what it refers to, the string is not dropped, which otherwise would have been true if we were just talking about string rather than reference to string. Okay, so one of the things that I'm going to insert an opinion, but I may have to change this opinion over time, but for the Rust that I've written so far, not just in the context of this book, and maybe it's my bias coming from a Python background, but I like references. I like having a reference to a string, a reference to something that's an int, a reference to a vector, so that I can do stuff, but I'm not replacing by taking ownership and saying, this is where this thing ends. There may be situations where you don't want a reference, where you want to pass by value instead of pass by reference. It does occasionally come up, but this is something that you might be looking at now and go, well, but why should I bother with reference? It's because it's very convenient in many ways. It can be very computationally efficient to do this and effective, and it can be one of those things where if you're trying to preserve memory safety and keep your options open to reusing a variable, that this is one of the effective default assumptions you can do. I'm not saying you should always do it, but I think it's something that is worth trying to keep in your toolbox for keeping your options open. Does that make sense? Hopefully that makes sense. So the scope in which S is valid is the same as any function parameter's scope, but the value pointed to by the reference is not dropped when s stops being used, because s doesn't have ownership. That's this s inside of the function. When functions have references as parameters instead of the actual values, we won't need to return the values in order to give back ownership because we never had ownership. Instead, there's a nice, lovely little kind of, you could think of it as a synchronization lock going on there, where you can borrow instead. So we call the action of creating a reference borrowing. As in real life, if a person owes you something, you can borrow it from them. When you're done, you have to give it back. You don't own it, okay? And Rust won't let you steal, all right? Just so you know. So what happens if we try to modify something we're borrowing? Try the code in listing 4-6. Spoiler alert, it won't work. Okay, so the first thing, not particularly knowing this example, that I can see is that we're defining this variable, let s, and we're binding it to the value of string from hello. And the thing I actually want to say here is that I don't see a mutability, semicolon. The s is not mutable. So when we're calling something like change, without even really knowing what they're about to tell us in terms of the error, because I haven't read it yet, although it's right there, you're probably reading it on the screen now. But I would say, look, I mean, the first problem is clearly a function that's called change, and then you do something like push stir inside of that function. Well, it's immutable, so you shouldn't be able to change it unless you assign it to be mutable, at the very least. Let's consider, though, whatever this tutorial wants us to consider. So we have the change function, we call it. Our first problem is that change is not defined, so let's have some fun and define change. So we've got some string, and we will give reference to string, not string itself, but reference to string. We're only going to pass in a reference, and we can go some string that we've got from our parameter turned into an argument, and we go push stir. We're borrowing, but to the borrowed value, we're going to go push stir. Okay, we're getting an error, but I think we've basically copied out their code. So what do we got here? What do we have here? We have cannot borrow some string as mutable as it is behind a reference of some string is a reference. So the data it refers to can not be borrowed as mutable. All right, but like you might not have considered this yet, or maybe you have, but like why couldn't we have like a mutable reference to string? Well, that gets a little tricky. Let's see. First of all, we would need this itself to be mutable because you can't change the unchangeable, but then also you have to write this kind of let mute string, and then let's see, we require a mutable reference to string. So I'm getting a little ahead of myself here with setting up this example, but what I was really just trying to quickly intimate without actually doing it correctly right off the first pass is that we want to be able to maybe take something and modify it. Right, so here's our error. Let's go back and fix our example. Some string push stir world. All right, and that'll get fixed up for us. And did we spell everything correctly? Let's see. Cannot borrow some string. Yeah, this is the error we had before. Good. Okay. So my overall point here is that mutability becomes part of the type, although I didn't show it well, and we will, I think, come back to that point. But let's keep going. So they've got this example. They tell us there's an error we should expect, which is it's kind of thinking that we should have a mutable string. Let's just double check that I have the correct error. There we go. It is error E0596, and you can see that that's the case here. We could explain it with Rust C if we want to. But let's keep going. So just as variables are immutable by default, so are references. We're not allowed to modify something we have a reference to, except, you might have guessed it because I was fiddling around with this, you can have mutable references. Now, it's important, and one of the things that I didn't ultimately do correctly was I needed to put mute, reference to mute s. So let's finish what I started and retype out the parts that were that I abandoned. But here we've got let mute s. We're saying that s itself is mutable because look, if it's not, then like how can you say that you changed a thing that is not allowed to change? I don't know how that makes sense. So we're going to have to make it make sense. For change, we're going to change other types. We're going to say this is not changing s. Otherwise, we would say something like just pass an s and it would be implicitly mutable, right? But here we're saying, well, no, we're taking a reference. We're passing a reference to s that is going to be mutable. And then also, this becomes part of the type for some string as well. We have to go reference mute string. That, again, I'll say, and maybe this is kind of a theme I should say about Rust, is that a lot of things become part of the type system. It's part of how they're using the type system to, I'd be tempted to say implicitly for us as Rust users, not for the people who wrote the compiler, but there are all kinds of checks to make sure that the Rust code is actually correct. So we've got fun, change, some string, mutable reference to string, some string, push, stir, and this is modifying the string itself. Let's run this. And it runs, but unfortunately, I don't think this example actually shows us anything. So let's say we got ourselves a little bit of let foo, because I kind of want to look at something. We could go print line macro, and then we could say, well, let's put a formatting placeholder there, and then a foo, and let's run that. And I have missed something. Help trait display. Because I'm modifying the string, but really the unit type is what's returned here. I did not think about this correctly. And maybe you caught it before I caught it, but really while we're changing s, we're changing it kind of in place, and that the return type of change is still the unit type. So instead, let's stick s here, because that's really what we changed in the first place. And there we go. We have hello world. All right. All right, so we've done that, easy peasy. First, let's change s to be mute. We're jumping back into the example. I often do this where I just look at their code and I start explaining it, but we're going to now say what they want to say because sometimes they correct me or add more context. So let's do it. Then we create a mutable reference with reference to mutable reference s, where we call the change function and update the function signature to accept a mutable reference with some string that has the type of mutable reference to string. This makes it very clear that the change function will mutate the value it borrows. Mutable references have one big restriction. If you have a mutable reference to a value, you can have no other references to that value. This is one of the borrowing rules. You can only have one mutable reference. You can have as many immutable references, and maybe we'll get to that, but it's a problem to have multiple mutable references. This code that attempts to create two mutable references to s will fail. Sounds a little grim, but let's give it a go. So we'll say let mute s be bound to the value of whatever is string, taking string literal from hello, make that a little smaller. Let r1 be bound to the value of a, where is it? Funny keyboard. Okay, so reference to mute s, we're not done. We'll say let r2 also be bound to mute s. Okay, well, that's kind of okay until we're going to get to the next part where we go print line macro, and we're going to say, what if we do a formatted print statement, print line macro. And now we're getting this issue with borrowing. Even before we run the compiler, because Rust Analyzer is wonderful, we cannot borrow s as mutable more than once at a time. Second mutable borrowing is occurring here. All right, so what happens if we run their example? We should get the same error that they say we should get, right? So let's go cargo run. And we get this problem. And it's exactly the same problem. They specify that the first mutable reference borrows here and the second one borrows there, and first borrow later used here, and that we are not allowed to do this. Cannot borrow S as mutable more than once at a time. Oh my goodness. So we could just take a little quick look, Rust C, and explain E0, and this is error 400 and, oops, 400 and, oops. So please note that in Rust you can either have many immutable references or one mutable reference. For more details, you might want to read the reference on references and borrowing in the book. Well, that's what we're doing right now, so that's not immediately useful, but they give us some more examples. I don't think we need to go through this example in more detail other than to say, look, it's going to allow for some cases where you've got, you know, a distinction between mutable references of some given variable. And as long as it's one at a time, it's actually fine, is basically what their example is saying there. But we're not going to go too far into that example. We want to stick to the book for now. Okay, so this error says that this code is invalid because we cannot borrow S as mutable more than once at a time. The first mutable borrow is in R1 and must last until it's used in the printline macro. And why do we say that? Because we access it for the last time here in the printline macro, which is going to, not the direct code printline macro because that's a macro, but rather the resulting Rust instructions. It's going to end up trying to take ownership of R1, but it's going to gain ownership of S if we're not careful, and also going to do it from R2, which is in this other position. So we can't do this. But between the creation of that mutable reference and its usage, we tried to create another mutable reference in R2 that borrows the same data as R1. The restriction preventing multiple mutable references to the same data at the same time allows for mutation, but in a very controlled fashion. It's something that new Rustaceans struggle with because most languages let you mutate whatever you'd like. This is true. You take a language like Python, you can not only change like the value, but you can change the type and all kinds of stuff on a whim. The benefit of having this restriction is that Rust can prevent data races at compile time. A data race is similar to a race condition and happens when these three behaviors occur. You have two or more pointers access the same data at the same time. At least one of the pointers is used to write to the data. And there's no mechanism used to synchronize access to the data. So that's what synchronization is about, whether it's like a binary mutex or a counting semaphore or various other kinds of synchronization mechanisms. You basically need to be able to access and modify data in a consistent fashion. So data races cause undefined behavior and can be difficult to diagnose and fix when you're trying to track them down at runtime. Rust prevents this problem by refusing to compile code with data races, at least of this kind of identifiable form. So as always, we can use curly brackets to create a new scope, allowing for multiple mutable references, not just simultaneous ones. All right. So let's take a little look at this. This is almost the same example. We can leave the mute S, but here we're going to stick this first creation of a reference inside of a local scope. And this is a thing that you can do in Rust that basically goes, I can create local scopes wherever I want just by adding curly brackets. This doesn't have to, it's not a function per se. It's not like a struct or any other thing, other such thing. It is just, you can create scopes with additional brackets, which I think is actually kind of cool because Rust's borrowing rules also apply, and its kind of lifetime rules also apply to these local scopes. It's actually quite great. So your issue here with your print statement becomes that you don't know, or the Rust doesn't know what R1 is anymore, because R1 in this example stops existing at the end of this scope. So there's no problem with this borrow. Like, we got rid of the error here by putting this inside of a local scope. But as I just said, R1 will stop being a valid variable at the end of that curly bracket that I have the cursor on. So that's a bit of a problem if you want to use it outside of that scope. Now, let's get back to the book. Rust enforces a similar rule for combining mutable and immutable references. This code results in an error. Yeah, let's try this out. So let's get rid of our extra scope variables. We've got, R1, S1, and let's get rid of these mutes so that we're just talking about reference to S, not mutable references, because the problem should be multiple mutable references. We should be able to have as many immutable references as we really like, or at least what the computer can handle in terms of resources. So let's let R3 be bound to the value of a mutable reference to S. Still not a huge problem. Let's see if this actually even gives an error. I don't think it will. We're getting warnings because we're not using these variables, but that's actually fine. For a toy example like this, we don't really care. You might want to get rid of those kind of statements for code where you have to compile again and again and you don't want to look at those errors. But here we're going to move on to our next step, which is we're going to then use the printline macro, which will require some simultaneous existence of these references, and that's where we will hit an error because we actually have a mutable reference as well as two immutable ones. So, cannot borrow S as mutable because it is also borrowed as immutable. Mutable borrow occurs here. All right, so we should get an error as they show. Let's run it. So we go cargo run. And there's our immutable borrow later used here, and mutable borrow occurs here, and immutable borrow occurs here. All right. That is an identical error to what we get. And the book says, woo. Woo. Sure. We also cannot have a mutable reference while we have an immutable one to the same value. Users of an immutable reference don't expect the value to suddenly change out from under them. However, multiple immutable references are allowed because no one who is just reading the data has the ability to affect anyone else's reading of the data. Note that a reference's scope starts from where it is introduced and continues through the last time that the reference is used. So for instance, this code will compile because the last usage of the immutable reference is the printline macro before the mutable reference is introduced. So we're going to shake things up a little bit where there's no particular problem with me. First of all, let's see, before that reference gets created, good. This should be no problem. Where we get, it's kind of awkward. Hello? Hello? Hello there. Hi. But that's because both of those references are immutable. I'm allowed to have, according to the Rust compiler, any number of immutable references that I like. It's the restriction on the mutable ones that's a problem. But the printline macro will result in code that takes ownership of R1 and R2, and they will disappear. So then, if I get to R3, and I say, let R3 be bound to a mutable reference to S, and then I printline macro that, I should not have a problem. There we go. Hello, hello. Hello. Wonderful. So the scopes of the immutable references R1 and R2 end after the printline macro, where they are last used, which is before the mutable reference R3 is created. These scopes don't overlap, so this code is allowed. The compiler can tell that the reference is no longer being used at a point before the end of the scope. Even though borrowing errors may be frustrating at times, remember that it's the Rust compiler pointing out that a potential bug early. That it's the Rust compiler pointing out a potential bug early at compile time rather than at runtime. In other words, fail fast, and showing you exactly where the problem is. then you don't have to track down why your data isn't what you thought it was. All right. Dangling references. In languages with pointers, it's easy to erroneously create a dangling pointer. A pointer that references a location in memory that may have been given to someone else by freeing some memory while preserving a pointer to that memory. In Rust, by contrast, the compiler guarantees that references will never be dangling references. If you have a reference to some data, the compiler will ensure that the data will not go out of scope before the reference to the data does. Let's try a dangling reference to see how Rust prevents them from a compile time error. Let's do it. So inside of our main function, let's go reference to nothing. We'll assign that to the value of dangle. Dangle is not a built-in name, function, whatever of Rust. So let's define a dangle function. And it is going to return a reference to string. And let's see. Let's declare a variable s from hello. And then let's return the reference to s itself. So now we're getting a lifetime specifying error. This function's return type contains a borrow value, but there is no value to be borrowed from. It's a map without a territory. Okay, so if we were to compile this, let's compile it just to see what error we get. There's our error, missing lifetime specifier, expected named lifetime parameter. We haven't covered named lifetime parameters yet, but it is trying to point us in the direction here of saying you cannot just return this reference to s, because s itself is going to stop existing or stop being a valid reference by the end of this scope, the end of the scope of dangle. So this error message refers to a feature we haven't covered yet in Rust, which is lifetimes. We'll discuss lifetimes in detail in chapter 10, but if you disregard the parts about lifetimes, the message does contain the key to why this code is a problem. This function's return type contains a borrowed value, but there is no value for it to be borrowed from. Let's take a closer look at exactly what's happening at each stage of our dangle code. So they're going to add some lines here, some comments. Here we've got dangle returns a reference to string. That's just this declaration of reference to string type. Then we've got s is a new string. This is just a let or a declaration of the variable kind of statement. And then we've got this reference to s where we return a reference to the string s. And then when we get to this curly bracket here, s goes out of scope and is dropped. So its memory goes away. Danger, like you're referencing to something that no longer exists. A map without a territory. Because s is created inside dangle, when the code of dangle is finished, s will be deallocated. But we've tried to return a reference to it. That means this reference would be pointing to an invalid string. That's no good. Rust won't let us do this. And, for good reason, for avoiding bugs and potentially security vulnerabilities. So the solution here is to return the string directly. And yeah, like if you're just defining a function in Rust where you want to create a value through calling a function like this, it is completely fine to do something like this. And now dangle will, actually, can I rename this to no dangle? Using some sweet, sweet LSP magic, we have no dangle, and this code should compile. Yeah, we get some warnings about an unused variable, but otherwise this is fine. There we go. Bueno. This works without any problems. Ownership is moved out and nothing is deallocated. So the rules of references. Let's recap on what we've discussed about references. At any given time, you can either, and this is not an either or, this is an exclusive or, one mutable reference or any number of immutable references. And references must always be valid. Valid in the sense of being still defined within the scope. And now we'll look at a different kind of reference, slices. We're not going to cover that in this video. We'll cover that in the next video. But this is like a more complicated idea of having a collection of references is what a slice basically gives you. It's kind of a fat, kind of fancy pointer thing, but we'll get there. So that's it for this video. Thank you for watching, and I will catch you in the next one. Take care.